Howdy folks, welcome to the first homework of the semester. Wowee! We're pretty much going to be going over all of the analyses that folks are supposed to learn in intro stats. So a lot of the material we cover here might be a bit boring, might be just very review for a lot of you, so feel free to skip around a little bit as long as you put together something for the homework just to show that you worked on this stuff. It's all good, but you know, you might just put it on in the background while you do exercise or something. Okie doke. So this past week we very briefly went over the different types of analyses that folks in intro stats learn. There's mean difference type of analyses, where you're just saying, okay, is there a difference in two or more means? And within that group there's t-tests, and the more complicated ANOVAs. T-tests can handle only 2 means, ANOVAs can handle 3 or more. There are association types of analyses, like correlations and regressions. These are all about checking, does one variable or do a set of variables move alongside with another one? So a correlation can handle just 2 variables, a regression is more complicated, it can handle 3 or more, and it can still do just the correlation stuff in the same way that the ANOVA can still do what a t-test does. However, regression and ANOVA are special in that there's a lot of different options that you have. There's a lot of different things that you can do. And in fact, a regression can do what every other type of analysis on this sheet can do as well. And we'll learn more about that in future, but to keep this short, I'm going to try and avoid any digressions. There's probability sorts of analyses. These are for checking whether there's a relationship between 2 categorical variables. So these often come about as a probability. Is there a higher likelihood of one thing given another thing's certain conditions? And the type of analysis there is a chi-square analysis. You can do 2 or more categorical variables with that. And validity checks, these are also called they're used for identifying different types of validity and sorry, I just completely lost the word, and I automatically go over to jamovi to check for what we're looking at. These are sorts of factor analyses. That's what I was thinking, and I don't remember why I didn't think that was right. Anyway, the point of these analyses is to check, do a series of variables adequately measure the same thing? So if you have like a 10-question survey about happiness, do all 10 of those questions measure the same thing? And really what's going on there is you're running a series of correlations to a regression. It's kind of a quick way to explain it, but suffice to say that it's basically a more complicated form of regression, and all it does is it tells you how reliable is your data set. It's a pretty straightforward set of type of analysis to run. There's more versions of any one of these subsets of analyses, and really these subsets aren't strictly how people talk about this stuff, but it is helpful to think about it kind of in this organization, because each one of these are 4 different sorts of questions that you're trying to answer on a theoretical basis. When you report the statistics for these, you'll find that there's a fairly consistent pattern with all of them. You will always get some sort of test statistic. So for the t-test, the test statistic is t. This is a number that indicates how strong of a relationship there is between the variables. In most analyses, you'll get df values, which is a number that tells you the sample size in conjunction with the complexity of the analysis. That's important because the more sample size you have, the more significant your results are. The more complex your analysis, the less significant your results are going to be. So the df value should be reasonably high for you to accept an analysis as a well-made one, but a lot of the times you can just look at the sample size in each one of the groups to double check that. Anyway, it's always a good idea to report the df, and that goes right after the t. By the way, on this slide, all these underlined bits are where a number gets plugged in. So you wouldn't put df here, you would put the df number. You get the t number. P-value is something that you'll get in almost every type of analysis. The p-value tells you how significant an analysis is, or how likely there is to be a variable relationship that is described by that type of analysis. So in this case, for a t-test, the p-value tells you what is the chance that there's a difference in these two means. And so if we get a p-value that's lower than 5% or 0.05, usually we say that's significant, meaning that there is a difference in the two means, or we're at least 95% sure that there's a difference in those two means. We will also have an effect size for most analyses. In the case of a t-test, the effect size is d, or Cohen's d. The effect size is a measure of the strength of the association between the variables, but unlike P and DF and T, effect size does not care about the sample size. And so effect size is kind of clean of any sample size issues. What does that mean? Well, if you have a big enough sample size, anything is going to be significant. If your sample is too small, nothing is going to be significant. But your effect size should stay almost at about the same number at all times, regardless of your sample size, given the same data. And that's helpful in understanding, does this result matter? We'll learn more about that in the future, and we'll get practice with it. But the last bit of a lot of analyses you're going to be running is some sort of interpretative information. For t-tests, those are means and standard deviations. That lets you show where the difference is. The t-test just tells you there is a significant difference. The means are going to tell you which one of the two numbers were bigger, and standard deviations are going to help you tell how much of a difference there is there. If you ever had a science teacher mad at you for not presenting the units in a set of data, they go, oh, well, how much volume do we have here? 15. You didn't put milliliters down, so I don't know what that means. When we're presenting any means, we should always present a standard deviation, because that's kind of going to be the units that we're working with. The standard deviation tells you how much number matters for that data set. For ANOVA, you'll notice that the stats that you get as an output are pretty much the same as a t-test. The variables here, the test statistic is an F instead of a T, but it still gives you a number, and you still have DF values. You get a p-value that works the same way, and an eta squared, that's your effect size, but it works in a very similar way to D. For T and for effect size, for test statistics and for effect sizes, bigger is always going to indicate a stronger relationship. However, the extent to the number is going to be different. For example, when we get down here to R, the numbers can go from -1 to +1. For D and eta, they go from 0 to infinity, but a larger D, say like a D of 1, is considered super, super huge, whereas an eta of 0.5 would be considered super huge. For ANOVAs, since you are comparing mean differences still, it's always a good idea to present at least 2 or 3 means and standard deviations again, so you can show what difference is and how big the difference is. Sometimes when we're presenting these means, we have a scale that we understand, like test scores. It's going to be between 0 and 100. A 10-point difference is a letter grade, so that's important. But we don't always know how meaningful things are. For example, with that same test score idea, if you're working with one particular student, 10 to 20 points is big. But if you're working with thousands or millions of students, a difference of just 1 or 2 points might be big for you. So again, that standard deviation is what's going to tell us how important of a difference we're working with. Okay, so for the association analyses, we have similar sorts of reports. We have a test statistic for correlations, that's R, and you get a p-value. There's no DF value for the correlation because the analysis is always going to be the exact same level of complexity. So really, you could report sample size alongside these two if you wanted to, and some people do. For regression, you really are going to have a huge variety of complexity in your regression analyses, but the reporting itself is not as complicated as you might think. When you're reporting an overall regression, you get an F, P, and R squared. and a df value as well. And this stuff should be familiar to you. R squared, it works a lot like R. It's your effect size in this case. Note that there's no effect size for correlation because R is kind of the test statistic and effect size rolled into one. Correlations are such a simple analysis that there's really no need for more output. The special thing that regressions are going to give you are significance values and numbers for individual variables. So regressions let you predict any given dependent variable from one or more independent variables. And so if you're trying to predict how much does 1 year increase in age affect your height or your weight, your regression is going to tell you, does that year increase in age, or does age matter for height and weight, or for just one variable? And the prediction formula is going to let you come up with a mathematical formula that tells you, okay, well, if you grow up by 1 year, you might gain ½ an inch of height, or something like that. That's the prediction formula. It can get a bit more complicated if there's more independent variables. When we're talking about the numbers in the prediction formula, we're going to call those B's or betas, and we'll learn more about that when we get to the regression chapter. So let's move on. In the chi-square analysis, we're working with two categorical variables, and the analysis itself isn't too complicated, so you really just get your test statistic and your p-value. There are df values that people report occasionally, but because we're working with percentages, df values don't always get reported here, since you'll usually just get a table telling you, okay, well, there were 15 people who were 7 years old and female, and there were 17 people who were 8 years old and female. And you get a whole table of those sample sizes, and those sample sizes are your df values. So again, df value here isn't really presented. The complexity of the chi-square analysis is always going to be entirely dependent on your variables and not on any statistical choices that you're making. So that's kind of why you don't always present a df value there. But you can if you like. Depending on the type of program you're using to run your analysis, you may or may not get it. Of course, you get a p-value for chi-square. The p-value is telling you that there may or may not be a significant association between your variables, pretty much in the same way that regressions or t-tests are going to do that. But for the interpretation information, you're going to get percentages. Like 16% of girls had blonde hair and blue eyes, 5% of girls had black hair and blue eyes. So that's going to take the place of the means or the prediction formula from these other analyses. And the thing with this is that you're going to have to choose which percentages matter to you, because the chi-square analysis just says that there is a difference in some of the percentages. Where the difference is not necessarily a question that can be answered, but you can say that I'm theoretically interested in blonde versus black-haired folks, so those are the percentages I'm going to give. Finally, validity tests, we're just working with reliability analysis for now. The only thing the reliability analysis is going to give you is an alpha value. You may have heard of it called the Cronbach's alpha, and this number just tells you how reliable your data are, how reliable your measurement set is. This number ranges from 0 to 1 in the same way a correlation can range from 0 to 1, meaning that 1 is the most strongest type of alpha that you can get. 0.7 is considered a decent strength, or 0.7 or higher. The only other thing that you can give really for your reliability analysis in terms of interpretation is what items you removed and what items you reverse coded. As you're running your reliability analysis, part of what you do is identify sort of bad questions or bad variables, and full disclosure analysis would describe which ones were bad or why they were bad, or if they just needed to be reverse coded. So what choices do you have for these analyses? In a t-test, there are 3 different types of t-test: independent, dependent, and one sample t-test. We'll go over those quickly because I'm assuming that folks here will know that, but I'm just going to cover it, just to cover everything. There are many, many different types of ANOVAs. We're just going to cover your basic ANOVA for now, but we will be getting more complicated in the next couple of weeks. One choice that you do have for your ANOVA is whether or not to run a post hoc test. So, well, I'll explain what that is moving forward, but the quick and dirty is post hoc tests let you know where the difference is given that there could be multiple or just one significant difference. For test of association, correlations are pretty simple. You don't really have much of an option there. But in regression, you have the choice of presenting which one of your independent variables were significant. This is going to be super important for the multiple variable regressions that we're going to be running this semester, but we're really going to gloss over that for now. Not really any options for chi-square, but when you run a reliability analysis, you have to choose whether or not you want to cull variables, get rid of the bad ones, or reverse code them, or if you want to leave them as is for whatever reason that you might personally have. To give you an example of when you might get rid of a variable, if you're just trying to make the best measurement you can, then you might get rid of all the ones that suck. If you're testing how good a measurement is, say someone else measured something with this 10-question survey and you think their survey sucks, so you just want to show that it's not very good. In that case, you might not get rid of any variables or change it all, so you can say the reliability of this survey as it was used is thus. Okay, so t-test options. You've got 3 types of t-tests that folks use pretty often: independent, dependent / paired, means the same thing, and one sample t-test. Your independent t-tests are going to be for 2 means that are not related to each other. So what is the height for boys versus girls? Your dependent or paired t-tests are going to be for 2 means that are related to each other in some way. A lot of times dependent t-tests are used for repeated measures data, like what is the difference in your height at age 14 and then again at age 15. But it can also be for 2 means that are related but not necessarily repeated measures. So what is there a difference in height between your mother's height and your height? So that set of means is definitely intended to be related, but it's not a repeated measures data set. Whether or not you consider something to be a related set of means is really going to be a choice that you make. In some cases it'll be more obvious, in some cases it'll be more muddy. Like, should we consider the mom's and the children's height to be related to each other? Maybe. What about grandparents and grandchildren? Probably. But once we start getting into like aunts and uncles or great-great-grandparents, whether or not there's a relationship there is kind of up to choice. It's important to note that that choice will affect how your results come about. When you run a repeated measures or any sort of related variables analysis, like a dependent samples t-test, you're going to have a more liberal analysis on your hands. What does that mean? It means that the same means with the same standard deviations are going to be more significant in a paired samples t-test than in an independent samples t-test. So there's a couple different reasons for that, but suffice to say that that's kind of one choice that you have. If you want to make things more significant, you might use a paired dependent samples t-test. If you're doing so unreasonably, you can kind of p-hack yourself there. So you can make things significant that really shouldn't be because they really should be an independent samples t-test. This last type of t-test, the one sample t-test, is not really used often all the time because it is a little bit cheaty. The way the one sample t-test works is you have one mean and you're just checking whether it's different from another number. So you're just saying, okay, well, is there a difference between my average test grades and 80? That's why it's a one sample t-test, because you're just comparing one mean to another number. Most of the times this one sample t-test is used when you have limited data source. Say you work for a company and they want to know, okay, well, is there a significant deviation from our expected product size in the actual products that we're making? And so they just give you a series of numbers that are the size they were expecting minus the size that they actually got, right? And so in that case, you're not really comparing 2 means, you just have a size and a number that you were hoping for. A lot of times one sample t-tests aren't used because in most cases in psychology we're actually working with 2 means, 2 different distributions. So When they do get used, it might be because someone is just trying to run a simpler analysis than they should. Say maybe they take the height of parents and subtract that from the height of children, and then see if the resulting difference score is different from 0. So in that case, if the number was different from 0, then you would say that there's a significant difference in heights between parents and children. However, doing so eliminates some of the data that we have. We have turned two distributions, two data sets, into one data set, and because we've manipulated that data, we've also lost some data, and that's going to be a little bit cheaty. It's kind of another way to p-hack. It's another way that you might find a result that isn't necessarily true. So one-sample t-tests are available, but not as often used in research and psychology. So let's go ahead and run these tests. I'm going to walk you through doing all of them in Jamovi. It's really not too complicated. We're going to be using a data set, and this semester we're going to be using this website StatCrunch to give us our data sets. This data set is from the National Survey, a National Longitudinal Youth Survey. It gathered data about children and young adults ages 14 to 20. We're particularly working with some weight data, so these teenagers had to evaluate were they underweight, overweight, and we're just going to use the first 100 data points for this data set. So what you'll need to do if you're following along, go ahead and double click on this stuff or triple click and copy and paste this into your browser. And once you've got that up, you'll get a data set. It sort of looks like this. Let's see if I can make it so we can see both things at the same time. There we go. Yes, I do have a lot of tabs open because that's just the kind of dude I am. The data set's pretty straightforward. You have gender, age, height, weight, and here's the question about weight. How would you describe yourself? Are you slightly underweight? Are you extremely overweight? And we're just going to use these first 100 data points because this is quite a large data set. To do that, I'm just going to click and drag down to the 100 line, and I'm going to, on my keyboard, hit Control-C to copy the information, open up Jamovi. You'll see I was already working with this data, but I'm going to open up just a new Jamovi just so you can see me do the whole process. So here I've got my Jamovi, and I'm just going to hit Control-V to paste the information in there. It should be fairly similar to the way you do this on Mac if you're working on one of those. Now we need to organize our variables. You can double click on these to bring up their menu, and we'll start giving them names. So we know the first one is gender, next one is age, then we have height in inches, and next we have weight in lbs. Finally, we have weight evaluation. I'm just going to call that WE for short. Now, each one of these variables, you'll notice, has a variable type, the little icon here in the corner, and we can choose the variable type that we're working with here as well as here. So for gender, we have words, female and male, so it's automatically picked text as our data type and nominal as our variable type. Note that this is going to limit the types of analyses that you can do. If you're trying to run an analysis and for whatever reason the results are wonky or it's not letting you, it might be that you've got a mistake in here. Jamovi makes it pretty easy to figure out what sorts of variables go where, but you can make mistakes still. It's not quite perfect. Okay, so next up we have age. Definitely age should be a continuous variable. And it's going to be an integer. Your other choice for numbers is going to be decimal. I would always recommend to record your data as only numbers. So in my opinion, the best thing to do here would be have females and males be like 0 and 1, and we would just call the nominal, and in here we could type in that if you had 0 and 1, you could type in, well, 0 means female. So if we go over here, say to this height in inches, we could say, well, 59 means short. And so it's going to label the height of 59 inches as short. Now in this case, we're not actually working with something that needs labels, so I'm just going to leave it as 59. Height should be continuous, of course, weight continuous, and our weight evaluation is going to be nominal text. You'll notice that nominal variables that are text have this little A in the corner to let you know that they're text-based. That's because the text-based variables have more limitations on them than just normal nominal number-based variables. Okay, so we've set up our variables here, and we can start running analyses. Now, the first analyses that we want to run are going to be, well, I'm going to focus in this class on answering research questions instead of running analyses. So the first research questions that we have are, is there a difference in height between boys and girls? Is there a difference in age between boys and girls? And I added in that S. And so the way we're going to answer these is with a couple of t-tests. So is there a difference in height between boys and girls? We're going to need to run a t-test. Jamovi makes it pretty easy to do so. There's a box that says t-test. Click on that, and you can choose the type of t-test that you want to run. We're going to run an independent sample t-test because boys and girls are not really related to each other. So to run that analysis, we have two boxes, one for our dependent variables, in this case we're working with height, and one for our independent variables, in this case we're working with gender. And you'll notice that in the corner here it tells you what sorts of variables can go in this box. Sometimes it doesn't force you to do that depending on the type of analysis for different reasons. So again, if it doesn't let you put something in there, say like it doesn't let you put age in there, in this case it says no, and it says no because it's not the right kind of variable. Okie dokie. Now at baseline, by default, this is going to give you, let's make this a little bit bigger. By default, Jamovi is going to give you just three numbers here: your test statistic, your t value, your df value, and your p. I'm going to request that you always get your effect size as well, and that you always have some sort of descriptives as well. So this is going to give you your means and standard deviations. The other thing is that anytime you run any analysis, it's always going to be helpful to look at some sort of graph for the analysis, and Jamovi should make that easy for you. In this case, there's a thing that says descriptive plots, and it shows us here in a graph where our numbers are at. So clearly males are taller than females. This also gives us a little range. So this is the mean, and this is going to be your standard error or your standard deviation, or in this case your confidence interval, and that just kind of gives us a range of where the mean could be. Because there's no overlap here at all, we know there's definitely going to be a significant difference, and that this is going to be a pretty huge difference. If we go back to the numbers, we see our test statistic is pretty big. The positive and negative doesn't really matter, but the magnitude does. So remember I said a t-value of 1 or greater is probably going to be significant. Here we have 7, which is ginormous. Same thing with your d. I said that 1 is considered a ginormous d, and here we got 1.4, which means we have a super ginormous effect size going on, and of course the outcome is significant, and we have a good sample size going on here. So how are we going to report this result? Well, here on this next slide, I've got kind of an answer to that. Is there a difference in height between boys and girls? What I'm looking for is for you to always kind of follow a three-step process in reporting the results. Tell me what is the analysis and the variables, so you introduce the analysis. Tell me the output, the stats and significance for the analysis, and tell me some sort of interpretation about the analysis. And we've kind of done that here. So let me just maximize this so it's easier to see. An independent samples t-test found that boys were significantly taller than girls. So here we've introduced the analysis, and we've got the variable, the independent variable here would be boys and girls, or gender. And here we have the dependent variable, taller obviously indicates height. So here in these boxes, these parentheses, we've got some numbers, and I'm going to request that you always put your numbers in parentheses because in my opinion and in my experience, having your sentences reserved for words always makes things a little bit cleaner. In this parenthesis, we've got our stats and significance that we're looking for, so t value, df value, p value and p, d and d value, and you can see where we got all of those here in this set of boxes. You can pause if you're looking for those or if you're walking through it yourself. Note that the letters here for T, P, and D are italicized. Any letter in a statistical analysis that is not a Greek letter should be italicized. and that is to differentiate it from variables that we might be using otherwise. In most cases, statistical variables, statistical concepts will be italicized all the time to let you know that we're talking about the t in stats. So you might have a t variable in your analysis or in whatever math you're running. Lastly, when we're reporting the stats and significance, here's the stats that I'm talking about. We're also going to have the significance. In this case, we are saying there's a significant difference verbally in addition to giving that number stuff. Finally, the interpretation part is all about these means as well as which mean is bigger. So if you give me the two means, you can tell which one is bigger, but I'm also going to say that boys were taller than girls. And so that's kind of the three parts. Introduce the analysis and the variables. Give me the stats and the significance. Give me some sort of interpretation. Okay, so next question, is there a difference in age between boys and girls? And because we're reporting another independent samples t-test, you'll notice that this is almost exactly the same as this with just a couple minor differences. Let's see what we've got. An independent samples t-test found no significant difference in the ages of boys and girls in the data set. When we're working with a lot of parentheses, and you will work with a lot of parentheses from now on, it's good to know that your sentence should read normally, assuming those parentheses were gone. So if I just get rid of these parentheses, this sentence should read as a normal sentence. An independent samples t-test found no significant difference in the ages of boys and girls in the data set, right? So oftentimes folks who aren't used to working with parentheses will write their sentences almost as if you're supposed to read the stuff in the parenthesis like it's part of the sentence. Don't do that. It's a very common mistake, and it just makes your writing a little bit less clean. The stuff in the parenthesis is supporting information that supports what you're saying there, right? And so this is the information that supports the significant, or in this case, the non-significant difference. Here's the supporting information that supports the interpretation that boys and girls were not different. And it's not a surprise that they weren't different because their mean is almost exactly the same. Okay, so how do we get these numbers? Once again, you get them by going to jamovi, and we can actually pop in age here as a dependent variable, and it's just going to run two different t-tests for us. So you can see that in this case, no significant difference. We have a pretty small effect size, and that effect size is really, really very small because we're working with very small mean differences here. Fun fact, when you calculate your effect size for a t-test, most of what you're doing is comparing the difference in means to the average or pooled standard deviation. So in this case, you can kind of estimate what's going on. Let's say, we'll do it for height because it's a bit bigger. So the difference in means here is about 4, and the standard deviation, the pooled or average standard deviation, is about 2.7. So I'm just going to take out my trusty calculator here I have in my hands. Actually, no, that's silly. I should do that on the screen for you. Calculator. So 4 divided by 2.7, you get a difference of 1.48. So this is telling you that the magnitude of the mean difference compared to variability in the data set is 1.48, or there's about 1.5 times more difference between the two mean groups than there is within any one of the means. So we get that 1.48, and the effect size that we get is here 1.47, pretty much the same thing. The calculation is a little bit different than what I just described, but you get the idea. Okie dokie. So we know how to report a t-test. Now let's see if we can run a dependent samples t-test. For the data that we're working with right now, we can't really run a dependent samples t-test. So just for this analysis, I've also pulled up another data set, in this case, height of mothers and daughters. Again, if you open up this link here, let's see, where do we have it? Here we go. So here's our mother and daughter data set. We're going to do the same thing. and just copy the first 100 data points here. And so if you copy those first 100 data points and paste them into Jamovi, get a new Jamovi. Paste it in, label the variables correctly, so moms, continuous, daughters, continuous, and let's run that dependent samples t-test. Again, this is going to be dependent because we believe that mom and daughter height should be related to each other. So we're going to pick, in this case it's called a paired samples t-test. Dependent, paired really means the same thing. Paired, not a surprise that it means the same thing because moms and daughters are paired, the variables are paired in this case. You'll notice the interface is a little bit different, but most of this stuff is pretty familiar. So we're going to pop in our two variables. Note that it doesn't really matter the order of variables that we get in there. The only thing that does is reverse the polarity. It just changes the sign on the test statistics and the D. So here we have -2 and positive 0.02. We change it back. Then we have +2 and the effect size in this case, it's pre-cleaned of that positive and negative for you. But oh wait, no. The P is never going to be clean, but the effect size would have been clean. My bad. Sorry. The P is never going to be negative because it is already just saying, is there a difference there, not which direction the difference is going. Sorry. For some reason, I thought that P meant effect size for a bit. To report this analysis, again, we want the effect size. We're going to want some descriptives and a graph to see what's going on. So here we see that daughters seem to have a lower mean of height, but that the means are sort of overlapping. When you read any graph like this with error bars, that's what these are called, when you interpret it as comparing this dot to the other error bar. So yes, these two error bars are overlapping, but because this dot doesn't overlap with this error bar, it's going to be significant. And you'll see that it is significant here, but it's not super ultra hyper significant, like it's not less than 0.001, still significant at 0.02. I will tell you right now and forevermore, if you ever have a significant effect that is between 0.05 and 0.01, you should be wary of that significant effect. Why should you be wary of it? Because it's probably not going to be very strong. If we look at our Cohen's D here, a D of 0.2 is considered a small effect size, and so we have a D of 0.23, which means that it's really not particularly big. By comparison, a medium effect size is, let's see, I think it's 0.5, and a large effect size is 0.8. So this is definitely a small thing. There's charts for how big each effect size is, or how you interpret the size of effect size, and we'll actually see where those are, and I'll make those available. You're not really intended to memorize them, but if you have done stats as long as I have, you probably will memorize them over time. So there you go. We also get our means. We can tell that this isn't a huge difference because the mean difference here is 0.6 and our standard deviation is, say, like 1.5, so that's way less than 1 standard deviation, and despite that being a small effect, it's still significant because we have a pretty sizable sample size. Okie dokie, so what is the report going to look like for this? If you're not too sure, it should be pretty much the same as it was before. I encourage you to pause and just try and guess what it's going to be here. But here's the answer in 3, 2, 1. Make that bigger for you. A paired samples t-test found that mothers were significantly taller than daughters. Means and test statistics. Although this is not repeated measures data, we expect the height of mothers and daughters to be related to each other, so we use the dependent samples t-test. Great. And I already talked about the effect sizes there. So again, I would be wary of this result. It looks like to me that it's only significant because we have a pretty big set of data. We have 100 mothers and 100 daughters. Okay. Let's get to ANOVAs. We're already at 40 minutes long. Sorry, this is going to be a bit of a longer video. Again, you can skip around if you like. The ANOVA test tells you, is there at least one significant difference in a pair of means? So if you have three means that you're working with, A, B, and C, a significant ANOVA could mean a difference between A and B, A and C, or B and C, or any multiple group of these. So at least one or more of these differences. The ANOVA only tells you, is there at least one mean difference? To find the specific location of that difference or differences, we use post hoc tests to tell us where they are. And post hoc tests work pretty much like t-tests. The only special thing about post hoc tests and about ANOVAs is that they are both designed with error correction in mind. If you run 5 t-tests, there's a 5% chance that you are making a type 1 error in each one of those t-tests. And so when you run 5, it's actually multiplicative. So it's actually 5% times 5% times 5% times 5%. But the result ends up being about 25%, a little bit more like 30% chance of type 1 error. The ANOVA and post hoc tests are specifically designed to keep that 5% error rate at the 5% error rate. That being said, if you run a post hoc test for 30 different pair comparisons, you will still have that danger of finding a spurious comparison. But in most cases, we don't really need to worry about that too much. So again, we're going to be using that same weight evaluation data set from before with just the first 100 data points, and we've got 2 research questions here. Is there a difference in height between ages? Is there a difference in weight between ages? So ages, in this case, we're going to use as a categorical variable. And since we already have the data set up here in my other jamovi file, it shouldn't take too long to run it. Again, we have our data set with just 100 data points. And now, right now, we want to use age as a categorical variable because the independent variables for ANOVA are mostly going to be categorical. If I try to run an ANOVA as is with a dependent variable of height, and we try to use age as the independent variable, again, it's going to say nope, 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 and that's because age right now is a continuous variable. So if I go back, change this to a nominal variable, now we're talking about age as 7 different groups of people, and now it's going to let me run the analysis. If you ever click off of an analysis, you can always click on it to go back to the option. So here's that t-test that we were doing earlier, here's the ANOVA right now. I'm going to put age in there as the independent variable, and what we get should be pretty familiar. We have F, which is our test statistic. We have 2 DF values in this case. The first is the DF for age, which tells us how complicated our independent variable is. In this case, it's 6 because we have 7 age groups, 14, 15, 16, 17, 18, 19, and 20. And we also have a residual or an error DF, so this tells us after considering how complicated our analysis is, how much sample size do we have? Since we have 100 data points and we had an analysis of level 6 complexity, we have 93 leftover data points that give us kind of degrees of freedom, and that gets a little bit more complicated. If you don't really know what that means, you're not going to worry about it too much beyond what I've already talked about. I just always try and elaborate because that should make things easier to remember. We have our p-value, and we also have 2 other things, sum of squares and mean square. Sum of squares, if you're familiar with what residuals are, sum of squares is telling you what is the total amount of error in the ANOVA. So what it does is it gets the mean for the whole data set and says, well, what is the total amount of difference between each data point and the mean, and it's squared to get rid of any negatives so that the total is a total number instead of 0. If you just added them up without squaring them, you would get 0 because the mean is inherently the midpoint, and so a positive and negative difference would cancel out. Mean square is the same thing as sum of squares, except this time it's divided by the amount of data points. So mean square is telling you for each data point, on average per data point, there is an error or a residual of about 17 for points, 17 numbers, 17 height number difference between that and the average. Again, if you don't know what that means, don't worry about it. We really are not going to need it in the majority of cases for the analysis. There are some options here that we're going to click on to make sure that we're running the analysis as fully as I would always like you to. Make sure you pick effect size. There's different types of effect size for ANOVA for different reasons, and we'll see that in future. We'll see why in future, so don't worry about them right now. Here's your eta squared. So this is the symbol for eta if you're not familiar with that, but you can just write eta squared. And we're going to also want to find our descriptive statistics. So we have a lot of options here. Descriptive statistics aren't super available, but whenever we run an analysis and we want a graph, which can kind of give us our descriptive statistics, we're going to get that from estimated marginal means. And so we can get a graph, plots of the variable age. And let me tell you what estimated marginal means is. When we run an ANOVA or a regression or a couple other types of analyses, what we're actually doing is creating an estimated model for our data. We're creating a prediction formula, like in regression, that estimates all of our dependent variable data points based on all of our independent variable data points. And so what estimated marginal means is actually doing is telling you, well, what are the means for the groups of age based on our estimated model. Marginal is a word that indicates each individual group for age. That becomes more useful when we have multiple variables because you might be having means for age, but also means for gender. Marginal tells you that we're talking about within gender age, or within age gender, as opposed to across gender. If that's confusing, again, don't worry about it. Try and keep this short because we're already at 45 minutes. Yikes. Here's the graph for the data that we're working with. You'll notice that most of these age points have a pretty similar amount of variability in their height range, but two of them, ages 14 and 20, have a huge variability in height range. Now, why is this happening? To understand that, we need to understand that the higher your sample size, the less variability you have. That's why your higher sample size is going to indicate more significant results because you have less apparent variability. Why would we then have a super huge variability for 14 and 20? My guess is that we just don't have very many people in the 14 and 20 age groups. And so if I go and double check that, I can go to data, and I could go and just count how many people we have here. But instead I'm going to go to analysis, explore, and descriptives, and I can actually get a frequency table for age. And so let's see how many of each age group we have. We have 18, 15-year-olds, 19, 25, 23, 20, 13 of these ages, but we only have one 14-year-old and one 20-year-old in our data set. And because we only have one, our variability is going to appear huge. The analysis is assuming that we have one data point and we are therefore very, very unsure if that data point is true. That's the same way that if you do something one time, you're not necessarily sure that it'll work out the same way because you only have one piece of evidence that that's what's going to happen. Despite that, if we look at our heights and ages, it looks like maybe there might be a difference between age 16 and 19, but no other differences there. It looks like 15-year-olds just happen to be a bit taller than 16-year-olds in this case. I would really have expected the 14-year-olds to be shorter than the 20-year-olds, but because we don't have very much data for our 14-year-olds, our analysis is going to be flawed. So let's take a look at the report. Before we report our results, we do need means and standard deviations for this data, and to do that, I'm going to click back on descriptives, get some stats, and I'm going to say that I want a mean, and we've already got that here. It's given us the median, minimum, and maximum by default, and how much sample we've got. Get rid of that stuff, but I also want my standard deviation. Now, the thing here is that we really aren't interested in the standard deviation and mean for age. So what we're going to do is look for this mean and standard deviation for height. I'm going to go ahead and pop in weight divided by age. And so that's going to go ahead and give us all those numbers that we want. Now, this is a complicated, unnecessarily large set of data, right? And reporting 1, 2, 3, 4, 5, 6, 7 means and standard deviations would be cumbersome. So if you're actually wanting to report this, there's a couple options. You could, A, report just a couple of means and standard deviations that are important to you. B, a much better choice, make a table that has all of this information and simply put a parenthesis, see table 1 in your output. Or C, make a graph. Some people say that if you have a mean in a graph, you do not need to report that mean in a table or in the text. Personally, I do not believe in that. I believe that any time that you can give means and standard deviations, you absolutely should. But depending on the field of research that you're in or the advisor that you're working with, there'll be different standards of reporting there. My side is almost always going to be on the side of give me everything. You'll notice that there are no standard deviations for heights for ages 14 and 20. That's because you can't have a standard deviation with one data point. There's no variance in one data point. There's just the one data point. Okie doke. So what are our interpretations, our reports going to look like? Take a moment to try and guess right now, but they're really going to be very similar to the t-test results. Is there a difference in height between ages? An ANOVA found a significant difference in height between age groups, while Tukey's post-hoc tests found no significant differences in the comparison between 16 and 19-year-olds. Sorry, I've kind of mushed it up here. While Tukey's post-hoc test found no significant differences, the comparison between 16 and 19-year-olds was closest to achieving significance. Despite this, sample sizes for 14 and 20-year-olds were too small for adequate analysis. So I've got here the quick and dirty result. It introduces the analysis and variables. Let's go ahead and fill in together the stats that go here. So I'm going to say parenthesis, and we're going to need an italicized F as well as a subscript. You do that by hitting Control plus on Windows, parenthesis, and in there is going to go the DF value. So if we go back to our ANOVA here, DF is 6, 13. 6, 13. Now we need to get out of the subscript, so hit again Control plus. It's the key right to the left of your backspace. Right to the left. Space. Now we put in equals and our F value located here, 1.471, comma, P, make sure that P is italicized here, 0.01197, comma, eta squared equals 0.087. When you are working, oftentimes you'll see this done. Instead of putting this superscript square, it'll just be eta 2. And people know what that means, but if you want to add the superscript, it's Control Shift plus. And you can just write out eta or find a way to put eta in there. There's a couple different ways. You can go to Insert, and there'll be a symbol button, and you can find the symbol in this list. There's also, if you just Google the alt code on Windows, Windows eta alt code, you'll find that there's always a number that represents stuff. So where's eta? There's mu. Where's eta? Did I type in eta? Nope. Eta. Give me the eta one. How do I write eta in Word? Here we go. Alt plus number pad 936. The number pad is the block of numbers on the right-hand side of your keyboard. So you can hold Alt and hit 936. That's going to give us, that's not eta at all. That's psi. Whoops. Where is eta? Find it in this list, I guess. glyphs. What? Greek alphabet. Here we go. Eta, 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 eta. Control F, ETA for eta. Ba, 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 ba. There we go. Alt 951. So if you hold Alt and then type and then numberpad 951, you get your eta. But you're not required to do that all the time. Okay, italicize that P. And there's our stat block for the ANOVA. Now, I've talked here about post hoc tests. How do we do that? We go back to jamovi, and click back on the, whoops, this is the wrong jamovi. Go back, click on the ANOVA. We can hit, this is a t-test. Where's my ANOVA? Is this ANOVA? Here we go. Click on the ANOVA. We can go to post hoc test and say that I want post hoc tests for age. It's going to give us a big table, and what this table is saying is here are all the pairwise comparisons for the age groups. Pairwise meaning two means. So the difference in height between age 14 and 15 was 3.8. Difference in height between 14 and 16 was 2.9. Yada, 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 yada. And it gives you the output for a t-test. Note that there are many types of post hoc tests, and they're each different levels of conservative or liberal. We're just always going to stick with Tukey because it's the most common type of post hoc test, and when you're reporting these, people will often just report the p-value, but it is important to say that we're working with Tukey's post hoc test. If you like, you could report the t the same way that you would a normal t-test in full. It's just not super common. You'll also note that there's a lot of post hoc tests that we're working with here, one for every possible pair of ages. You do not ever want to report all of these things, and you pretty much don't ever want to put them in a table. If for some reason it's very important to report all of these, you can put them in a table. But in most cases, I would report them in batches. If we look through our p-values, you can see that there really aren't any significant post hoc tests. Now, why is that? Well, here we have no significant difference, so I would expect no differences in these post hoc tests. The closest one to being significant was between 16 and 19, and we already saw that down here in the graph. Closest possible difference. But if there was a difference, it would have been between 14 and 20. However, the data is insufficient for that, and so you'll notice that the post hoc test for 14 and 20 is super not significant because we have huge variability because we have very low sample sizes. So when I reported those post hoc tests, it looked something like this. While Tukey's post hoc tests found no significant differences, p is greater than or equal to 158, the comparison between 16 and 19-year-olds was closest to achieving significance. Despite this, sample sizes for 14 and 20-year-olds were too small for adequate analysis, and sample size equals 1 for those two. I've also reported the full Tukey's test here, given means for those 16 and 19-year-olds, and here I've done the batch reporting that I was talking about. Because the closest post hoc test to being significant was 0.158 for the 16 and 19-year-olds, I reported that one, and I said that all other post hoc tests were equal or less significant than that one. And that's what I've done here. That's a quick and easy way to report a bunch of tests without having to report a bunch of tests. Okay. Next research question, is there a difference in weight between the ages? And ANOVA found a significant difference in height. Whoops, you can tell I just copied and pasted this in. Put that in, weight. Between age groups, while Tukey's post hoc tests found no significant differences, the comparison between 16 and 19, blah, 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 blah. So I've just pasted this in. Let's go ahead and make the changes that we need to fix this, so I can show you where each one of those things come from. Again, if you've already run the analysis, there's no need to run it over again. We're just going to take height out and put weight in, and all these options are going to be the same as they were before. If we watch it work, you'll see it's populating those post hoc tests, and the graph looks pretty similar to the previous graph with problems in the 14 and 20 age range. Doesn't really look like there's huge differences. There might be a difference between like 15 and 18-year-olds. if we check our ANOVA results, there's no significant difference there. Effect size is teeny tiny, and there's really no significant post hoc tests because nothing was significant. You'll note here that the test statistic is 1.67, so that's not a it's not a small test statistic. Remember, higher than 1 is usually going to be significant. However, because there were so many groups, there's 7 groups here, this is not enough to be considered significant. Note that the complexity and the sample size matter here for that stuff. All right, so let's fill this stuff in. I'll make this bigger so that you can see it as we're filling in, and because we really don't need those, whoops, we really don't need those options. Go away. Okay. Oh, there we go. So we're going to be filling stuff in. We replaced the dependent variable already. Let's replace the f here. Why is it missing that? I don't know. Missing the df. So I can just put f parenthesis 6, 93. You'll notice that the df numbers are the same because we're working with an analysis of the same complexity and the same sample size. Replace that f value, 1.673, between age groups. Tukey's post has found no significant differences, so let's find the smallest, closest to being significant Tukey's post hoc test. Isn't this 0.4? Yes, I do think so. So the most closest to being significant is the 0.41. So we'll put that in. P is greater than or equal to 0.4. We're always going to report things to 3 decimal places. If you haven't got 3 decimal places in your jamovi, there is an option for it here at the top right, those 3 buttons. You hit number format and choose 3 decimal places. Okay. The comparison between, in this case, it was 15 and 20-year-olds. That's closest to achieving significance. P is 0.400. T is negative 2.035. Negative 2.035. And let's fill in those means. Let's get the weight ones only so it's not confusing. So, not 12-year-olds, 20-year-olds. Mean is 132.111 pounds. And standard deviation is 25.693. 20-year-olds mean is 200.000, comma. Standard deviation is not available because there is only one data point. Despite this, sample sizes for 14 and 20-year-olds were too small, n equals 1 for adequate analysis. So this is something that you probably were not taught in your previous stat courses. This is something where you are saying the analysis is not really very good because the sample size is not super good, same as we were doing last time. Moving on. When we run a correlation, oh gosh, we're already at 1 hour and 3 minutes. Sorry. I'll just really encourage you guys not to watch the whole thing if you don't want to. A correlation analysis, check for an association between 2 variables. We already described what a correlation does. As one increases, the other increases. Height would be correlated from age 0 to 20, but height would probably not be correlated from age 20 to 40 because people stop growing around that age. That being said, people probably have a correlated height and age between 60 and 80. Notice that from 0 to 20, you're going to have a positive correlation because people are getting taller as they get older, but from 60 to 80, you're going to have what's called a negative correlation because people are probably going to get shorter as they get older. Those correlations look like this on a scatter plot. You have your x and y axis, age and height. You'll see that there's on average a top right diagonal trending relationship there. That's positive correlation. A down right trending relationship is a negative correlation. If the relationship looks random between those 2 variables, that's called no correlation. if you're going to put a line here, it would be a flat line here across, which means that age and height weren't associated to each other. So this is what I would expect for 0 to 20-year-olds. This is what I expect for 60 to 80-year-olds. This is what I would expect for 20 to 40-year-olds. Note that correlations do not care about scale. Age and height are obviously going to be on a different scale, and if you run a correlation between age and height in inches and another correlation between age and height in feet, you're going to get the exact same correlation, even though height in inches and feet is completely different. Inches would move much more quickly, there would be a much larger numerical difference across the age groups. The correlation would be exactly the same, because what the correlation is looking at is just how much do the two numbers move together, not the extent to which they are moving. So correlation is kind of devoid of scale matters for the most part. By comparison, t-tests are all about scales because you're comparing means, and so the specific differences in the numbers are going to be what you're looking at. Correlations give you a test statistic R, which ranges from negative to positive 1. Both 1 negative and 1 positive mean perfect correlation. The two variables are the same thing, with ranges closer to 0, meaning there's weaker and weaker relationships. So let's run correlations. Is height associated to age? Pretty straightforward. Again, we're going to go back to our data set. We're going to go to regression, and within regression, pick correlation. We're going to say, oops, we're really not supposed to be doing this data set. We're going to go back and do this. We're going to say, okay, is age related to height? And you'll notice that this requests a continuous or a ordinal variable, but it's taken age as well. Technically, in some situations, you can use nominal variables for correlations, but it pretty much should always just be two continuous variables. Here's our results. The R is 0.24, p-value 0.016. So significant, but not particularly strong. And again, because this is higher than 0.01, I would be wary of this result, and I would expect that there's a significance, mostly because there's a large sample size. Let's take a look at the graph of the correlation to confirm this. So each of these little pluses is a data point. There's the line, and this gray is the kind of range where we would accept the line to be, and you'll notice that the vast majority of data is outside of that gray, meaning that the vast majority of data doesn't lend itself to a correlation. That being said, there is a little bit of a positive thing going on. If we ask for some more options here on the plot, we can get a little thing that shows how dense our data is. So this looks pretty normal to me. We're not going to worry about it. What about the stats? What can we get from the stats? There, give us our correlation so I can show us that. This is much more useful when we're running more complicated sets of correlations. Like in this case, we're running correlations for these 3 variables, so we have 3 correlations and 3 stats for that. Okie dokie, how are we going to report this? Pretty much the same way that you would expect. We have an R and a p-value. Let's put that into a sentence. A significant positive correlation was found between height and age in children. R is 0.241, P is 0.016. Now, if I was running this analysis for myself or for someone else, I would be wary of this result because it's weak and it's not particularly significant despite being a large sample size data set. So you might put in a sentence, despite this, you might just say, a significant, though weak, positive correlation was found, if you really want to stress that. But if you wanted to kind of, not necessarily p-hack, but influence people to think this matters, you could just put a significant positive correlation there, and that makes it seem like this is a huge thing, when really it's not. We found a significant result, but it's not really big, not really impactful. If we run the correlation for mothers and daughters' heights, pop that in, we get a correlation of negative 0.119 and a p-value of 0.237. Look at the correlation. Again, it's going to be small, and the dots really don't look like they're super associated to each other. This line is almost horizontal, which is not a surprise because this Pearson correlation is flat and it's not significant at all. So what does the report look like? No significant correlation, positive, that should be positive. No significant correlation was found between height and mothers to daughters. Okay. So, why would these two not be associated to each other? It's, to me, what that suggests is that maybe there are many more important factors than just mother's height to explain daughter's height, like the father's height, the family height, the environment in which they're raised, how much food they were able to eat when they were growing up, whether or not they experienced any duress, extreme stress during growth, or even drinking coffee can reduce your growth. So there might just be other variables. That being said, I would expect this to become significant with more data, just like anything would become significant with more data. This is telling us the interpretation here, if you wanted to really add more, would be, well, there wouldn't be any interpretation, but if you wanted to add an interpretation here, it would be that as age increased, so did height. Simple. And if this was significant, it would be as mother's height increased, so did daughter's height. But this is not true, so I wouldn't leave that there. Okie doke. Regression. Regression is going to work pretty much the same as correlation and ANOVA, and you'll see what that looks like. The extra quality for regression is that it can predict dependent from independent variables. Let's see what that looks like with questions. Is there an association between age and height? Let's run a regression. Regression, linear regression. Whoops. Okay, regression, linear regression, and pop in age as our independent variable, covariate, and height is our dependent variable. Now, even though this is not labeled as a continuous variable, it takes it, because it knows that it's at least a numeric variable that could be a covariate. What does covariate mean? It means continuous independent variable. We can actually use categorical or nominal independent variables in a regression. In this case, it's calling those factors. We're not going to cover that until we get to the regression chapter. What results do we have for our regression? To get that, well, let's see what we get for starting out. We have an r and an r squared. R squared is our effect size for the regression, and we see that it's not super huge. An r squared of 0.25 is considered large, and an r squared of 0.01 is considered small. So this is between small and large. 0.09 is considered medium. So it's not a big one, not a big effect size that we've got for our regression. We do, however, have a significant effect of age. When you report your regression, this is not what you're going to want to look for. You actually want to go to model fit and ask for the overall model test. This is going to give you the output for the overall regression. This is giving you the output for individual regression variables. And you'll notice that if we include other variables, you'll have multiple different significant effects. Again, we're not going to work with that until we get to the multivariate regression section, but just so you know why you get this, when you're reporting your overall regression, you want stuff from here. And what you get is your F, DF, P, and effect size in the same way that you get it for an ANOVA. You'll notice too that what we're doing here is an ANOVA. And why are we doing that? Because we're pretty much seeing, is there a difference in any of these age groups for the dependent variable? Again, if we want to look at a graph of this information, we go to the estimated marginal means, and that gives us a graph. Shows us pretty well that there's definitely a positive relationship going on there, and that's pretty much everything that we need. So what is the report for this going to look like? A regression found a significant association between age and height. Great, report those numbers. How tall is the average 14-year-old? Well, we are already running this regression for age and height. And so the relationship there has already been found. It's the exact same. The regression found a significant association between age and height. But to answer this question, we need a second part. Height increased by about half an inch on average for 14, this sentence could be better, on average per year of age. And I misspelled intercept, whoopsie. So full sentence here, height increased by about half an inch on average per year of age. So 14-year-old participants were estimated to be 64.463 inches tall, or about 5'4". These numbers here are from our regression prediction formula. They tell us that for every age increase, every year increase in age, people grew by about half an inch, 0.613, and that by default, to start or at 0 years of age, people were 55 inches tall. Now, of course, people who are 0 years of age are not 55 inches tall, but because we only have data for 14 to 16-year-olds, the intercept of the data is not the intercept that you would expect for age. What does this formula look like? It looks like this. X times 0.613 plus the intercept, 55.811, equals y. This should be familiar to you. Y equals m x plus b. Oftentimes this formula will be written in a slightly different organization. 55.811, the intercept, plus age times the number that we've got. In here, what we have is actually something called B1. And instead of the intercept, what we have is something called B0. And Y. So we put X there. This is the kind of raw version of the formula. And what it says is that B0, the intercept, plus X times the slope of X is equal to Y. Where do these numbers come from? Let's look at our regression again. Make this a little bigger because we don't need to see everything. In this box here, we have the model coefficients, or the estimates for those numbers. So what we've done in the regression is create a model that estimates the relationship between age and height. And the way that model works is that it's a line with some given slope and some given intercept. Here's the slope for age, here's the intercept. So at 0 point, we're still at 55, and at age whatever, multiply age by 0.613 to get 64.463. Okay. Chi-square. Chi-square tests are used to check for the likelihood of events under certain conditions. They're generally used when dealing with one or more categorical variables, such as the relationship between hair color and eye color. Oftentimes, people will use chi-square tests to make sure that they have met some preliminary requirements, like they randomly sampled people with hair and eye color types. So you could see was there a relationship between those two things, or was there an equal amount of men and women who had the different types of hair color? When you run a chi-square, you're just seeing if there's a relationship between the two variables, not necessarily where the relationship is. Let's take a look at a couple questions. Were men and women equally likely to label themselves as overweight? Were age and gender sampled randomly in this study? Okay, so we're going to go find men and women, and we're going to run a frequency test for independent samples chi-square. You'll see that it says chi-square there, test of association, and we're going to put men and women compared to weight. Okay? All right. Men and women, and the weight evaluation. It's going to give us a table of numbers, and what this table says is there were 17 females who evaluated themselves as slightly overweight, 21 about the right weight, 4 slightly underweight, blah, 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 blah. It's going to give us a chi-square test. Here's your chi-square value, test statistic, DF, and P. That stuff is going to get included here In the report of the result, a chi-square test found no significant association between weight evaluations and gender. Chi-square, PF of 4. Chi-square number of 8.7841. 8.781. P-value of 0.067. Not significant, close to being significant, but not quite there. And then our interpretation. Females were about as likely as males to label themselves slightly overweight, though low sample sizes may have caused an underpowered study. So, if we look at these groups, you'll notice that some of the groups have very few results. There are many rules of thumb for how much sample size you need in a chi-square test, but often and not, the most common would be to have at least 5 or at least 10 results in each cell, which means that we would want to have at least 5 or 10 in each one of these boxes for this analysis to be considered adequate, but over here we do not have that, so we don't have enough data to really get an idea of what's going on. To come up with these percentages, you can actually go to cells and look for row or column percentages. I'm going to ask for row percentages. So this is telling me 37 or 38% of females were here, 46% of females were here, 8.9% of females were here. When you interpret your chi-square, you kind of want to make a T. So we have the percentages for the rows, so what I'm going to compare is female versus male percentages within one of these. And I've done that here. Females were about as likely as males to label themselves slightly overweight. So if you go over here to the slightly overweight column, 37% of females and 23% of males, which apparently is not a significant comparison. And it's obvious that it's not a significant comparison because even though there's a difference here of like 15%, the actual size of that difference is between 13 and 17. Most times folks will just report a percentile for chi-squares instead of means, but this time I've given a sample size indication so that people can tell that things are screwy. And I've also written sample sizes were screwy. So the study may be underpowered. We'll learn more about what underpowered means in another class. Were age and gender sampled randomly in this study? A chi-square test found no relationship between age and gender, though low sample sizes indicate an underpowered study. So to do this, go put gender, go put age, and it works pretty much the exact same way. Okay, last bit, reliability analyses. As a reminder, a reliability analysis is used to check whether a whole set of measures is reliable, whether all 10 of our questions actually relate to happiness. I've already kind of talked through this stuff, so I'm just going to skip it for now in favor of the practice questions. Do age, weight, and height measure an overall growth construct? Do the 5 questions from the openness scale measure an overall construct reliability? So to answer the first one, we're going to use the data set that we've already got. We're going to go to factor analysis and a reliability analysis, and we're going to pop in these 3 variables. And we're going to check, do they come up with an overall growth variable? Now, these are kind of silly variables to pop in together, and not a huge surprise, they're not particularly strongly reliable. Remember, a strong reliability is going to be 0.7 or greater, so 0.142 is not the best. When you run a reliability analysis, you always have the option of improving your reliability by checking which of the variables were good or bad. To do that, you click on this Cronbach's alpha if item is dropped. And that tells you that if we get rid of height in inches, Cronbach's alpha would be 0.046. That is not an improvement, so we're not going to drop height in inches. If we drop weight in pounds, Cronbach's alpha goes up to 0.24281. So that is an improvement, which means we're going to drop weight in pounds. Now, why weight in pounds is not a very good variable is kind of up to your own interpretation. You could say that height and age are definitely associated to each other, but that weight could be variable. You can have a different rate regardless of your age and regardless of your height. Yeah, definitely weight and height are related to each other, but age is definitely not, and it seems as though height and weight are a little bit less related to each other than height and age are, so that might be why you could get rid of it. Get rid of it, now our complex alpha is better, and we check this list again. None of our variables need to be removed to improve our result, so our final result is an alpha of 0.281. And if we go check our output here, that's what we get. A reliability analysis found that age, weight, and height measures did not reliably measure an overall growth measure, and that the most reliable measure was achieved after removing weight from the measures list. Cronbach's alpha equals 0.281. Okay, how do we do this last question? Do the 5 questions from the openness scale measure an overall construct reliably? I wanted to get something that is a better representation of a reliability scale, and we can't really do that with the data that we've been working with so far, so I'm going to bring up one last data set. To get to this data set, you go to Jamovi, and we can actually open data sets by clicking on these 3 little lines, hit open, and there's going to be a data library here. If you ever have a missing data library, just click up arrow and it'll get you to the folders. By default, Jamovi gives you these 4 data sets, and you can actually download more data sets through the Jamovi interface. I've already got this module installed, but let me show you how to install modules. You go to the modules, Jamovi library, and there's a list here of modules that are available to use. We're going to be using some of these modules over the course of the semester, so it's important for me to teach you this at this point. We're going to look for 2 modules that we want right now, the Learning Statistics with Jamovi module and the R Datasets module. Both of these are datasets that are going to be useful when we're practicing our stats stuff. Once we've done that, you can click off it, going to the up arrow, open this up again, and hit the up arrow here to refresh this, and you'll notice that again we have more folders here because we have more data available. If you ever need to open data that you have yourself, you can click on this PC and browse through your own data files. Okie doke. So go to, I think we need to go to Learning Statistics with Jamovi. Yep. And scroll all the way down. We're going to work with this personality questionnaire down here. In this personality questionnaire, which usually takes a little bit to open up, we've got data from the Big 5 personality questionnaire. That's got 5 variables to represent agreeableness, openness, extroversion, neuroticism, and one more. Agreeableness, openness, neuroticism, extroversion, and I don't remember the last one. But it's taken its sweet time. Oh, there we go. It just finished opening. And each one of those variables is divided into the 5 questions with the letter to indicate. Oh, conscientiousness was the last one. So do the 5 questions from the openness scale measure an overall construct reliably? What we're going to do is go to factor analysis, and we're going to pick those O questions, pop them all in, and we get Cronbach's alpha of negative 0.094. Not very good, but it is giving us some help. Note, items O2 and O5 correlate negatively with the total scale and probably should be reversed. We can reverse code things easily here by going to this reverse coding thing and selecting O2 and O5. What does reverse coding mean? When you make a scale, you might have a question for happiness that says, like, on a 1 to 10 scale, how many times do you smile per week? But if you have another question that says, on a 1 to 10 scale, how many times do you frown per week? Those 2 questions have the same 1 to 10 scale, but the scales do opposite things. For the smiles question, a higher number means more happiness. For the frowns question, a higher number means less happiness, which means that we would need to reverse code one of the 2 so that they both are on the same scale. And we've done that here. That's what it was telling us about. We've done it here for questions O2 and O5. That improved our Cronbach's alpha immensely. We're still not quite at a perfect, or at least a reliable, by most standards, alpha. So let's double check, see if we can improve the alpha by getting rid of any items. It tells you that we've already reverse coded O2 and O5, this little superscript, but let's see, can we improve our alpha by getting rid of anything here? O4 definitely seems to be a problem child, so we're going to kick O4 out. It's improved our alpha. Can we improve it anymore? No. So the best reliability score we could get was 0.649 by getting rid of 1 question and reverse coding 2 more. So how am I going to report this result? a reliability analysis found near reliable, found that the openness questionnaire approached reliability after reverse coding items O2, whoops, O2, that's not O, O2 and O5, and removing O4, period. Let's make sure that we include the Crondox alpha to support this statement. Alpha equals 0.649, and we're done. Okay, it took an hour and a half, but I've successfully covered everything that people should have learned in intro stats. I'm going to go ahead and wrap up this video now so I don't waste more of your time, and if you did watch all of it and it was super boring, I'm very sorry, but at the very least, you might have gotten a free lulling to sleep. Okay, I'll see you guys next week. Ciao.